Hi guys, so for this video I'm going to be covering some concepts and I'm going to be showing how to convert a nomenclature name for a molecule into a Fischer projection, and how you can do back and forth from name to Fischer projection, or regular straight chain to Fischer projection and back. So I guess I'll just start with the Fischer projection, since that's part of the nomenclature and I didn't do that last video. But if I'm taking from the 2016 old exam, and so what she's gonna do, she's gonna give you a name, and you're going to have to convert it to a Fischer projection. And there's more than one way to do this, but it's pretty simple, really, and nothing really complicated about it, besides the fact that you need to just make sure you're careful about the RNS stereochemistry. Okay, so she'll give you this name, and the first thing that I like to do when I get the name is I like to convert it into the actual structure itself. So I'm just going to do that really quick. All right, so here's the structure. So it's pretty easy. So I have, let's get the pin out. So I have, always start with drawing out the parent chain. So the parent chain is hexane, so that's 6 carbons long. So 1, 2, 3, 4, 5, 6. Okay, this is not supposed to be there. All right, so 6 carbons long, and on carbon 2, right, I have on carbon 3 I have a bromo, and then carbon 2, 2, 2, 4, 5, 5. So I have 2 methyl groups on 2, 1 on 4, and 2 on 5, and this is our chain. Okay, just ignore this part right here. Okay, so and she gives you the stereochemistry. This is the most important part. You can't have a Fischer projection if you don't have stereochemistry. Like, there's nothing that is gonna be beneficial about doing a Fischer projection if you don't have stereochem. So the first thing you're gonna do is to set up your Fischer model. So we have 2 chiral centers, so that means your Fischer projection is going to have 2 cross points. So I have 1, 2, and each one of these is going to resemble a carbon that's going to have a chiral center on it. So I have 2, that means I have 2 cross points. Okay, so what I'm going to do, she tells you this is on carbon 3 and this is on carbon 4. So carbon 3, this is carbon 4. This is carbon 5 down here, and this is carbon 2 up here. Okay, so on carbon 2, right, this one right here, it has 3 CH3 groups. So carbon 2 is this one, and it's CH bonded. It's not CH, it's just C, and then it's bonded to CH3, 3, okay, and then on carbon 5, right, it's a carbon bonded to CH3, 3 as well. Okay, and this is going to be our basic, this is going to be our chain. So one of these carbons is carbon 1, and one of these carbons is carbon 6. So I have all 6, and now all I have to do is just fill in the remaining places. So that's to fill in one of these, not this one. So I'm on carbon 3 and 4, where my chiral centers are. So I have to fill in the Br, to fill in the hydrogen, and I have to fill in the hydrogen over here, and I have to fill in the methyl and the Br, right? So carbon 3 has the Br and the hydrogen. So what I'm going to do is I'm going to put the Br and the hydrogen in any random location. Okay, I'm not going to think about it. I'm not going to think too hard about it. And for carbon 4, I'm going to put the CH3 and the hydrogen in random locations. All right, and I'm doing this because I'm not gonna, think about, which way, where should I put it so that I get R, where should I put it, so that when it flips, it becomes R or whatever. I'm just gonna do it, and then I'm gonna check my stereochemistry, and if I'm wrong, I just flip the locations. So for the first one, this is gonna be 1 because bromine is heaviest. All right. And if I'm comparing this carbon to this carbon down here, this carbon is attached to 2 other carbons. This carbon is attached to 3 carbons. So this is my 2, this is my 3 down here, and this is my 4. Right? So 1, 2, 3, 4. This is going to be R, but because my hydrogen's on, on one of the horizontal positions, it flips to S. Okay? And then for this one, my number 1 carbon over here, I have 3 carbons, is going to be, this is going to be 1 because this carbon over here is attached to a bromine, a carbon, and a hydrogen. This carbon over here is attached to 3 hydrogens. This carbon down here is attached to 3 carbons. So the one with the bromine is going to be number 1. This is going to be 2, and this is going to be 3, and this is 4. So for this one, I go 1, 2, 3. So I'm going in this direction. So this is also R, right? I'm going around, I'm going clockwise, so 1, 2, 3, and this is going to also flip to S. So basically, for both of them, I have gone to S. So on my actual Fischer projection, what I need to do is I need to draw this out. I need to have the same thing. So this is carbon 2. So carbon 2 is attached to, I'm not interested in drawing all the crap again. Okay. And then carbon 5 is attached to also the 3 groups. Okay. And then I need to flip these. So I need to bring the hydrogen over here, the Br over here, and I need to bring the CH3 over here, and the hydrogen over here. And this should give me R and R. So just if anyone wants to check, this is 1, right? And I said this is 2, right? And then this is 3, and this is 4. So I have S at first, and it goes to R. Well, is what I want. And then down here on this center, I have this carbon down here is this one is up here is 1. This down here is 2. There's 3 over here. So this is also S, and it goes to R. So essentially, it's just a little bit of guess and check, and you just fill in the positions, and you'll get the right answer if you do it right. If we check the answer, I'm looking at it, and it looks exactly like what I have. So this is her answer. Come on, this is the answer on the exam sheet. So she has my H, Br, CH3. C, CH33, C, CH33. Okay, so it's very, very simple, and you shouldn't lose any points on such a simple problem like this. All right, so now let's look at the next part of the test, the facts section. Okay, so she has, I'm just going to take from her 2016 exam, and just gonna look over some stuff. It should be all based on like understanding of the reaction and understanding of double bonds, understanding of carbocations, carbanions, carbon radicals, just all the things that you should be familiar with already. So number 1, the last steps in this process of alcohol dehydration are shown below. Draw the structure of the lower energy transition state. Okay, so draw the structure of the lower energy transition state. So what we have over here is basically some concepts of how to translate some language. Okay, so essentially she's giving you 2 reactions, right? And on a graph, on a reaction energy graph, so you have energy over here, and then you have like time or whatever. Okay, and essentially what she has is a so every time you have a product, you have a so you have a starting point, okay, and then you have that climb, right? You have that climb to the top is the intermediate, okay, and then this is the trough is the product, okay. So we start from one thing and we go to one product, and then this thing goes to another thing, and it goes to it's another thing, and it goes to another product. All right, so I have two intermediates, right, and then I have a beginning material, I have a middle product, and I have an end product. Okay, and the thing about this is what we're doing is she's asking, draw the structure of the lower energy transition state. Okay, so what that should mean is, obviously I just made this graph from like my own kind of like just randomness, not accurate, but essentially the lower energy transition state is going to be reflected by the one that's not. So if I'm accurate about this, right, this should be higher. Okay, if I'm reflecting this one, this should be higher than the second one, okay? Because she says slow rate determining step, so that means this first step of the reaction is the part that has the highest amount of energy to overcome to form a transition state and to break the transition state and go from reactant to product. So just making this uglier. So this means that this transition state up here is going to be a lot higher energy, obviously, than the other one, right? So the one that we draw is a transition state that is formed as this molecule is going to this molecule. So the process of this molecule is present right here, and then its transition state between this and this, between, so I'm going to call this A, B, C, right? So A is here, B is here, C is here, and then A, B is up here, and B, C. So this means transition state. So this one is going to be the lower energy one because this is the fast step, and fast step means that it requires less energy for it to reach this peak than the other one. So this is the lower energy one. So I have to draw the transition state between going from this to this. And if I look at what changed, essentially, is I had a bond that's coming to the hydrogen, and then I have a bond that's breaking and forming a double bond, and that's essentially what's happening. So what's being drawn over here is all the, so when we draw bonds breaking and forming, we draw, like, for example, if I have let's say I have HCl and I had like OH, and I had this coming over here, blah, 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 and like this. And I would depict this whole thing essentially like this. I would draw to the hydrogen, and then I would draw like to the Cl. So this depicts bond breaking and bond forming, and that's what we're going to do. So we're going to draw the CH3CH, and then the line that was already there, CH2, and we're going to draw the H. So these bonds, the double bond was formed, so I'm going to draw dash, dash, dash. Hydrogen bond was broken, so I'm going to draw dash, dash, dash. And then the OSO3H is forming a bond to the hydrogen, so I'm going to put a dash, dash, dash there. And then I'm going to put partial positive and partial negative charges where the charges originally were. So I have a positive charge and I have a negative charge, so I need to put the partial charges at the location. So over here I would have a partially negative charge because this is negative, okay? And this doesn't have a partial charge. So that's essentially that question, okay? It's, you don't have to worry about the graph too much, but it helps me understand the slow RDS and the fast step over here, and how to convert this language into figuring out what's the lower energy transition state and why you don't draw the AB one, okay? So that's essentially that part. She may ask, draw the higher energy transition state. In that case, you draw the AB one, right? So now that's gone out of the way. Now let's do number 2. Number 2 says, place the following alkenes in order of increasing quantity of heat evolved per mole in a catalytic hydrogenation reaction. So what is catalytic hydrogenation? Catalytic hydrogenation is something that's catalytic, so I have some sort of catalysis, right? So of hydrogenation, so hydrogen aiding. So I'm adding hydrogen bonds to the molecule wherever they can be added. So the only place where I have an unsaturated carbons is on that double bond. So I'm going to saturate them with hydrogen essentially. And so what this is saying is, I need everyone to think about, so the quantity of heat evolves. So heat is going to be evolved in exothermic reactions, right? And a reaction is exothermic in this case, right? So I start from something that's high energy and I go to something that's lower energy, right? So that's exothermic. So I want everyone to think about this. And the first one, and we talked about this before, right? The more carbon substitutions on a double bond, the lower the energy is, right? And the less carbon substitutions on a double bond. Okay, I don't know why I'm doing that, but the less carbon substitutions on a double bond. So if I had just all these bonds and I had hydrogen, 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 and then only one methyl group, this would be much higher energy. So using this concept, I'm gonna categorize the substitutions of these double bonds. So I have, all right, so I have this is tetra, so I'm gonna put T, and then this is 1, 2, so this is di, and put D, and this one is 1, 2, 3, so I'm gonna put, okay, I'm gonna put tetra, and this is tri. Okay, so tetra, so it means 4 carbons attached to a double bond. This is 2 carbons, this is 3 carbons. So this tetra one is going to be the lowest energy. Therefore, if I do this reaction, it's going to evolve the least amount of heat. So like if I were to draw a graph for each and every single one of these, from left to right, if I had 3 graphs, right, the tetra one would look something like this. Okay, I'm not saying it's going to look like that, but let's just imagine. Then the tri one is going to look something like this. Okay, and then the di is going to look something like this. So if I look at the amount of heat, so the amount of heat evolved is the difference between the start and the finish points. So as I decrease my substitution, the amount of heat is going to be increasing that is being evolved. So that's why the di one is 3, this is 2, and this is 1. So increasing quantity of heat evolved. So it's not that bad just to think about it a little bit, and it'll make a lot of sense. All right, so let's do some more problems. Let's see what else she got. She has 2 more. Alright, so 3 and 4, she has placed the following carbanions in order of increasing stability. This is all from Bean's exam, 2016. Increasing stability, so carbanions are opposite of positive charges and radicals. So positive charge and radicals, we prefer tertiary carbons over secondary, etc. And for negative charges, I prefer primary over secondary over tertiary. Okay, so I really want as few carbons around here, because that will, the more carbons I have around this negative charge, the more unstable it's going to be. So that's why you have the ordering like this. So this is a tertiary one that's drawn on the key, this is a primary one, and this is also a primary one, but the difference between these two is this is a primary with resonance. So obviously, okay, the first thing you're going to look at the degree of the carbons, right? But the thing that helps it more is if I can do resonance. So if I can delocalize a charge, that's going to be a lot better than always than having a charge sitting in just one location. So a fixed charge is always worse than a delocalized charge, no matter primary, secondary, tertiary. And usually it won't get so complicated. You have to like compare too many things, but resonance is always important. And the more resonance structures you have, the more stable it's going to be. So this one is primary with resonance. That's why this is 3, this is 2, and this is 1. All right. Now let's look at this. So consider the following carbocations. If the carbocation will rearrange, place a Y in the box. If the carbocation will not rearrange, place an N in the box. So carbocation rearrangement is a concept that is based off of mechanism, and I haven't done a mechanism synthesis video yet because, you know, basically covered it in class. Only if you guys ask me to, I will. But essentially, there's 2 things that can happen with carbocations, right? You can, including ring opening and closing, but it's sort of rearrangements. Okay. So let's say I have a positive charge over here, and let's say I had these methyl groups. One thing that can happen is a methyl group can shift. So this is called a methyl shift, right? And it will come over here to help stabilize this positive charge, right? And in nature, these things happen if the product of it is either just as stable or or more stable, right? That makes sense. For something to happen, it should result in a lower energy state. So and the same thing applies to hydrogen shifts. So if I have a positive charge over here, and let's say I had methyl group and I have a hydrogen, this hydrogen can shift over here to help stabilize this positive charge, and that's because this positive charge will now shift from a secondary carbon to a tertiary carbon. Okay, so it's going to somewhere that's going to be more stable for it, and that's essentially what this question is asking about. So for the first one, I have a carbocation, and next to it is a carbon group that has 3 carbons attached to it and a hydrogen. And so essentially I can do a hydride shift over here. It's stable. I'm going from a secondary carbon to a tertiary carbon. Okay. And this one, the answer is no, because my only adjacent things are hydrogens on centers that are exactly the same, and there's no reason why that would happen. There's no real benefit to moving the hydrogens to that location and moving the positive charge elsewhere. So this one would be no. And then the last one, I have a carbon that has four carbons attached to it, and next to a carbon that has a carbocation and only 2 carbons next to it. So something that will help stabilize this molecule more is if I do a methyl shift and transfer the carbocation to a location that has be a tertiary carbon at this point. So I transferred from a secondary carbocation to a tertiary carbocation, and so this is definitely something that's helpful, right? So it makes sense, right? Aside from this, I don't really think there's many other facts that I have to worry about. Let me check another exam real quick. Okay, so there are some more facts that I actually would like to cover. So let's take a quick look at some of these. So let's look at this. This is from 2015, I believe. And the answers are here, unfortunately. But let's look at number 2. So place the following alkenes in order of increasing stability. So this would seem like it's the same thing as before, but however, now we have alkenes on what we call bicyclic compounds, and there are certain rules for these bicyclic compounds. Okay, so normally we just look at the substitutions on the double bond and that's it, right? But if I do look at that, I get sort of seemingly conflicting answers. So for this one is a disub, this one over here is a tetrasub, and this one over here is a trisub. Okay, so normally you would think, wow, this should be 3. Why is this 1? And the reason for that is the location of the double bond. And the rule for this is if your double bond is what we call on the bridgehead carbon, right, attached to the bridgehead carbon, it must the bicyclic compound must be at least I believe 7 or more carbons all the way around the ring. So what this means is this double bond is in a location that we call in the bridgehead carbon location, and for it to be stable in this location, the whole ring itself has to be more than 7 or more, I believe. Okay, so what that means is if I count all the way around the biggest ring that's containing this double bond carbon, right? So yeah, what that means is I either can go around here or I can go up and include these. So either I trace this and I go and count these, or I go and I count these. So if you count the ones in the bottom, right, so it's the bigger one, obviously, it's 1, 2, 3, 4, 5, 6. So it's 6. It's not 7 or more. So it's not going to be stable. So automatically, this is 1. Okay? And if I compare this one and this one, they're not bridgehead. So that means it's regular rolls. This one's tri, this one's di. So this is going to be the most stable compared to the others. All right? So just remember that rule, the bridgehead carbon rule for bicyclic compounds. All right, now number 3, place the following halides in order of increasing reactivity in an E1 process. Okay, so what is E1? E1 is the elimination reaction, and it favors, right, to have tertiary over secondary over primary carbocations that form. Okay, so what this means is I'm going to do the E1 process, and I'm going to essentially make every single one of these leaving groups leave. All right, and I'm going to be comparing the carbocations that form. So what I see over here is that I'll get a positive charge over here, I will get a positive charge on the double bond over here, and I will get a positive charge right here. So this is a tertiary carbocation, this is a primary carbocation that forms. Obviously the key is already saying that. And so if I just had to compare these two, I would know right away that tertiary is much more preferred than the primary. So this is definitely better than the last one. So the right is currently better than the last one. Okay, now this one is interesting. So I form a secondary, technically carbocation, but the thing with this though is I form a carbocation in a really crappy location. This location is on the double bond itself, and I cannot perform any further reactions really on that location. Those carbons already, they're sp2 carbons, and you're not allowed to do any s2 on sp2. So I don't think the location is very receptive for any nucleophilic attack or anything like that. And I can't even resonate. So the no resonance is going to be able to go in that location either, right? So the carbocation is essentially fixed there, and that's the main thing. The carbocation is fixed in that location, and it's kind of just stuck. And because it's stuck on that double bond, and nothing can really be done to the double bond, I can't do E1 there because I already have a double bond present. So I can't form 2 back-to-back double bonds. So essentially, that carbocation is stuck, and it produces, the molecule is just very unstable at that point. And so number 1 over here is going to be this one, because how unreactive and how unfavorable it is to get this Br to leave, and it doesn't really happen. So this is going to be 1, this is 2, and this is 3. Okay, so if you're ever forming charges on a double bond, that's really undesired to happen, unfavorable. Okay, let's look at number 4. This is something you should know from the last exam, but I'll just read it. Place the following alkanes in order of increasing bond association energy. Bond association energy is homolytic cleavage. So what that means is it will have an even splitting of a bond, and each atom that was participating in that bond gets one electron from the original bond. So that's homolytic cleavage. That's what bond dissociation is. And then bond dissociation energy is the amount of energy that that it will take to make that happen. So how much energy you have to put in to cause bond dissociation. Okay, so essentially all we're doing is I'm looking at the rule that carbon radicals prefer tertiary over secondary, etc., etc. So this carbon right here is a carbon attached to one other carbon, so this is a primary carbon. This carbon right here that the hydrogen is attached to, right, is attached to two other carbons, so this is a secondary carbon over here on this carbon right here. And this carbon right here that this hydrogen is attached to is attached to three other carbons, so this is a tertiary carbon right here. So tertiary over secondary over primary, right? And I have all these over here. So I have primary, so this is a 1. Okay. This is going to be the most unstable if I form a radical there. So this is going to be the one that requires the most energy to be inputted so I can have that occur, right? So the more stable the product is, the lower energy and the less energy I have to overcome and put in, right, to form the radical. So this is going to be 3 because it's going to be the most unstable. This is 2. This is 1. All right. So nothing too crazy. But I think that should be the gist of what most of the concepts are for the facts section. You'll either have like compare the reactions, or you'll have double bond stability. You'll have some sort of carbocation radical or carbanion, or essentially have a mix of those, and she always has a transition state problem as well. The only problems that are kind of tricky are the ones where she says is something chiral or achiral, and those do take a little bit of stretching your mind a little bit. So the one on my exam was particularly kind of tricky. This is my exam that I took during my sophomore year. The chiral problem that she had on mine looked like this. Okay, and I think I'm pretty sure I guessed on this one, right? And she says label the compound below as chiral or achiral, and it turns out to be chiral. It looks extremely, Okay, first thing first. Even right now, I look at this and her explanations make perfect sense to me at this point, right? The rings are in perpendicular planes because they're too bulky. It's too much steric hindrance, so obviously they're going to be moving around, and there's not really a plane of symmetry. They look like there's going to be a plane of symmetry, but there are some chemical interactions that prevent that from happening so nicely and perfectly. But back then I didn't understand all that high level of understanding to look at this and be like, oh yeah, there's steric hindrance, obviously, no plane of symmetry. I'm pretty sure most 80% or more didn't think of it like that. What I did was I'm pretty sure I got this right by guessing, educated guess. And I looked at it and I said, okay, this is just way too obviously set up to look like, oh yeah, obviously there's a plane of symmetry. This would have been way too easy. And essentially led me to think that there has to be something, with the way this looks, that prevents it from being achiral and actually having a plane of symmetry. So if you just kind of try to avoid I'm actually looking at my exam right now if I got that. Yeah, I got it right. Right. Yeah. If it just looked way too set up for it to have a perfect plane of symmetry, and I just put chiral for that. And really, just usually it won't be too bad. If you do all the exam questions, you should be able to, have enough exposure to figure these out. All right. So that's the end of this video. Just remembering your concepts and just think it through. Remember the energy diagrams; they're extremely important. If you understand that, you really will easily understand a lot of things about organic chemistry. All right. I hope that helps. Let me know if you guys have any questions. All right. Bye.